Okay, so let's begin our foray into general relativity and black holes and so on and so forth. We'll also be using some GR concepts when we talk about cosmology. So, general relativity, as you probably know, is our modern theory of gravity. It supplanted Newton's theory of gravity. It agrees with Newton's predictions to very high precision in weak gravitational fields, but it doesn't ever exactly agree with them, similar to like with special relativity, right? In other words, the momentum is really always m gamma v, but it gets closer and closer to just being mv at low speeds, right? In other words, Newtonian mechanics is a low speed approximation to relativistic mechanics, and it's not sometimes one applies and sometimes the other applies. No, really it's, relativistic mechanics is always a more complete and better description, but on the other hand, it's harder to use, and so we will use Newtonian mechanics when we can get away with it. Similarly, general relativity is our modern depiction of gravity. It's qualitatively very different from Newton's picture of gravity, and it's always more right, if you will, than Newton's theory of gravity is. Nevertheless, that doesn't mean that we use it to pilot interplanetary probes, for example, because it's much harder to work with mathematically than Newton's theory is. But we will develop general relativity because it's beautiful, and it gives us insights into the nature of reality that nobody ever had before. So we're going to start with a mystery, which maybe you didn't realize was a mystery before. Mystery! Why do all objects have the same gravitational acceleration? Why do they all have the same acceleration in a gravitational field, independent of mass? Mystery. Why do all objects have the same acceleration in a gravitational field, independent of mass? Same acceleration in a given gravitational field. Independent of mass. And you know this, right? The idea that all objects fall at the same acceleration in Earth's gravitational field, for example, independent of their mass. And again, you may not have ever thought that that was a mystery, because the explanation, if you will, is that the gravitational force, the weight, is proportional to the mass. If you double the mass, you double the gravitational force, and therefore you're going to get the same acceleration. But that's the mystery. Why is it that if you double the mass, you double the gravitational force? So, in other words, here's cute little m, there's big M right there, and we know that according to Newton, the gravitational force is given by what between those two objects? If r is the distance between them, what's the gravitational force that they exert on one another? Yep, and then you multiply that by big G. Yep, big G. So G m, little m, over r squared. And so the acceleration of m is going to be given by A equals F over m. Well, that's going to be G big M little m over r squared times 1 over m. And m cancels out, right? M cancels out. And so you just get gm over r squared independent of m. Independent of m. And again, you knew that, right? This is not something you haven't seen before. But if you think about it, let's consider like electric charge, right? If I have electric charge, I'm going to go zoom out because I don't want to have to keep erasing over there. So I'm going to zoom out the view for the camera here. If I have electric charges, there's little q, there's big Q, there's a distance r between them. What's the force on each of those charges that they exert mutually via Coulomb's law? What do we write for Coulomb's law? Coulomb's law. Oh my God, do I have to go tell Dr. Trees you don't remember Coulomb's law?
It's the charges multiplied over the distance squared multiplied by a constant.
Multiplied by a constant, right. What's that constant?
It's 4 pi epsilon naught.
Stand on your head and say it.
No, it's 1 over
4 pi epsilon naught, yeah, right. Which we sometimes just call K, which I'll do right here, right? So the force is K times Q times little q over r squared. Mathematically, those are the same as one another, right? Mathematically speaking. So notice that we have this situation, but if we looked at the accelerations, well, the acceleration of, say, charge little q here would be this divided by its mass, right? So in other words, it's not the same that the acceleration in an electric field is the same on all objects independent of their mass, because what the force depends on is the electric charge, which is different from the mass. But gravitationally, according to Newton's law, then what we can see here is that in Newton's theory of gravity, let's see. But the problem is, I need to bring myself over here for Kathleen. There we go. I got to keep remembering that. There, okay. In Newton's theory of gravity, mass plays the role of gravitational charge, if you will. It's the property of a body that couples it to gravity, that says how big the gravitational force is going to be. Just like electric charge couples to the electric field to say how big the electric force, the electrostatic force is going to be. Now, when I was first introduced to this, I had a little trouble at first getting the point. Like, why is this mysterious? Is that true for you? Is it like, so, mass is what couples to gravity. That's just the way it is. And if it is not, if you're having trouble seeing why that's weird, let me ask you this. Could you conceive of a situation where two objects had the same, well, let me put it this way. Let me say some more here before I ask this question. So, can I move you back over, Kathleen? I'm doing it, okay? I'm moving you back over here. All right. What we should do here, try to get far enough away. So what we should really do here separate the idea of mass as gravitational charge and the other notion that we have of mass in terms of inertia, right? In other words, Newton's second law says that acceleration is force over mass, and mass is the property of a quantity in this sense that gives it inertia. What is inertia? Define inertia.
The tendency of the object to move.
It's not the tendency of the object to move, it's about resisting something.
It's the resistance of the object to change.
Yeah, it's right. Mass, in terms of inertia, is resistance to acceleration, right? So really, what this is what we should call the inertial mass. The property that gives the body resistance to acceleration. The larger the inertial mass, the smaller the acceleration for a given force. So let's be explicit about that. Let's say that m sub I will be the inertial mass of a body, the thing which you divide the force by in order to determine its acceleration. And let's say that we'll call m sub g, not mg, m sub g, the gravitational mass. The property that determines how much force is on the mass due to the presence of a gravitational field. The property that couples the body to the gravitational field, just like charge couples a body to the electric field, gravitational mass couples a body to the gravitational field. And determines the gravitational force on the body. Questions at this point? So then, I'll wait for people to catch up. So then, oh, people are still writing. I haven't waited enough for people to catch up. What's that?
You can keep going.
I can keep going, yeah, well, okay. So then, what we should do is write that the inertial mass times the acceleration in our gravity problem again, right? So we're back to little m, big M, distance r between them. So here's m sub I. And well, here's this body here, and it has, well, let's say, has possibly two different masses. Its inertial mass and its gravitational mass. And we should say that the inertial mass times the acceleration should be equal to the gravitational force, but that's going to be g times m times the gravitational mass divided by r squared. In other words, m sub g says how much gravitational force is on it, and m sub I says how it responds to force in general, so that then the acceleration would be g m sub g over r squared times m sub I. But of course, we always find that the acceleration is independent of the composition of the body, et cetera, et cetera. And so normally we just say, oh, well, we can cancel these two quantities. Here's my question. Can you conceive of an experiment you could do that could show that one and the same object had a different gravitational mass than its inertial mass? So how do you measure inertial mass? So remember, inertial mass is what tells you resistance to acceleration. So how would you do an experiment to determine something's inertial mass?
Apply force and measure its acceleration.
Right, apply an unbalanced force to it and measure its acceleration as a result of that. That'll determine its inertial mass. And how do you determine its gravitational mass? Well, the gravitational mass couples it to the gravitational field. So what do you need to do to figure out what the gravitational mass is?
Measure its weight.
Yeah, you measure its weight, right? Because weight is the gravitational force, at least in the Newtonian view. And so when you step on a scale, what are you measuring? Are you measuring your inertial mass or your gravitational mass? You're measuring your gravitational mass. But if you wanted to measure your inertial mass, why, you should have somebody pull on you with a rope and see how much you accelerate or something like that. Well, here's an approach. So question, can I erase this yet? No, okay, because I don't want to keep moving around to show it to Kathleen. So, and I'll just wait till everybody's got this written down. Okay, anybody going to stop me here? Can I do it? Can I do it? It's going to go, all right. Okay. All right, so where's more colored chalk when you want it? I've got red and orange. I want like blue or something like that. More variety here. Right, of course. I want colored chalk. There's no colored chalk around. All right, we'll just go with red and orange here. Okay. What did I just draw? Spring system, right? That is a if there's no friction there, why that's a simple harmonic oscillator, right? I mean, of course, I'm going to make a simple harmonic oscillator, right, or a simple harmonic oscillator, as I like to think of it. Okay, so if I stretch it, let's say that the spring constant is K, and let's say that the mass of this block is m, and let's ask a question here. If I stretch it and then I let go, what's it going to do? It's going to start, yeah, but will it keep going?
No friction again.
Yeah, no friction. So it'll execute simple harmonic motion, right? And you remember, it'll be described by its angular frequency, omega naught squared, is equal to, how's it related to K and M? Do you remember? Well, one can show that it's K over M. Omega naught's the square root of k over m, so omega naught squared is k over m. M inertial or M gravitational? Inertial, right? Because it's its resistance to acceleration that is determining what the angular frequency is going to be. The larger the mass, the more slowly that thing's going to oscillate because it's more sluggish. It's harder for the spring to shove it around. So this will allow you, this would be a way to measure the inertial mass using this spring. You could measure the inertial mass this way. If you already knew the spring constant, then you could just figure out what the angular frequency was and use that to determine the inertial mass of that block right there. How could I use the spring to determine the block's gravitational mass? Yes? Hang it. Yep, hang it. So I can use the spring to get them both. I could also connect it to the spring. Okay, so now I want to find out what its gravitational mass is. And if it has stretched by some distance x past the equilibrium length of the spring, then what will be the force exerted by the spring on the block if I've stretched it a distance x past equilibrium? What's Hooke's law say? That you're getting too much energy in this. Yeah, F is minus kx, right, for Hooke's law, right? The force is proportional to the displacement. Okay, so what would the equilibrium condition be here? What would be force balance saying? Again, we're in Newtonian's world, we're in Newton's world here. So what's the downward force on the block? Right, and so if we're in the vicinity of Earth's surface, well then we just take big G times the mass of the Earth divided by the radius of the Earth squared, and we call that
Gravitational force.
not gravitational force. Yeah, if I'm in the vicinity of Earth's surface, I can take big G times the mass of the Earth divided by Earth's radius squared. And here we're ignoring subtleties like Earth is rotating and stuff like that. Those are small corrections, and also Earth doesn't have a single radius, blah, blah, blah. But big G, mass of Earth over radius of Earth squared, we put all that together into, we do, and what do we call that? What's its value? 9.81 meters per second squared, right? That's the acceleration due to gravity in the vicinity of Earth's surface, right? Really that little g, 9.81 meters per second squared, that's essentially big G mass of Earth over radius of Earth squared. So the gravitational force, according to Newton, would be the gravitational mass times g, the acceleration due to gravity in the local gravitational field. And meanwhile, there's also an upward force, kx, where x is the spring constant. And so we could figure out the gravitational mass by saying that the amount that it stretches, x, will be given by mgg equals kx. And so then you could just solve for mg. So I could use the same spring and horizontally figure out the inertial mass and vertically figure out the gravitational mass. How then could I go about the following? I want to know if the gravitational mass and the inertial mass are the same for this block right here, and let's say I attach it to the spring and I discover that its gravitational mass is mg, just like for the red block. The orange block and the red block both have the same gravitational mass, mg. What could I do to show whether or not their inertial masses are also the same? I mean, we've laid it out. What's my next step? Put it back on the horizontal spring, right? Put the spring horizontal, shake it. If their gravitational masses are the same, what's the signature that their inertial masses are also the same? What will I notice about how fast they shake back and forth when I attach them to the horizontal spring?
Should go for as long as the other one.
Well, what I'm looking for is the oscillation period or the oscillation frequency, right? The oscillation frequencies would be the same if the inertial masses is the same. But could you at least imagine that you'd hang two blocks, a red one and an orange one, they stretch the spring by exactly the same amount, so they weigh exactly the same, and then you put them on the spring mounted horizontally, and one of them jiggles back and forth twice as fast as the other one. That would tell you that the one that jiggled back twice as fast, back and forth twice as fast, had a smaller inertial mass, even though they had the same gravitational mass. Can you at least conceive of that happening? I'm not asking you if it ever would happen. I'm asking you if you can conceive of it. You could do the experiment and discover that two objects weighed the same but had different amounts of inertia. One was easier to shove around than the other one. You could at least conceive of that, right? Does it ever happen?
I want to say no.
Yeah, that's correct. The answer is no, it never happens. Experiments will always show you that if two objects have the same gravitational mass, they also have the same inertial mass. That's the mystery, and that's what I want you to be able to do, is understand that that's a mystery, because is it not true that inertial mass and gravitational mass are two very different things? One determines how much something is pulled on by gravity, and that has nothing to do per se with how hard it is to shove around. And the other one is telling you how hard it is to shove around, which has nothing to do per se, you might think, with how hard it's pulled on by gravity. Just like with charges. How hard a charge is pulled on by the electric field has nothing to do with how much mass that object that carries that charge has. So why is gravity different? That's the big mystery. This is what we would like to understand. And what does this have to do with general relativity? Well, Einstein said that the happiest thought of his life was when he realized that somebody who jumped off of a roof would not feel their own weight. And that thought, thinking about the implications of that, led him to general relativity. And so this is what we want to understand, is why is the fact that if you jump off of a roof, you don't feel your own weight, how does that lead to general relativity? Because believe it or not, it does. Okay, what questions do you have? There's a lot to think about here. There is, right? In other words, it's kind of seemingly simple, but you've probably never thought about it before, that, well, why is it that it's mysterious? Maybe you never even thought it was mysterious, that, well, you just accept it. And the first time I saw this, I'm like, what's the big deal? Gravitational force is based on the mass. So what? No! So what? What? It's so important, all right? Okay? Are you ready to take this to the next level? All right, let's do it. So, let's work on that idea that if you jump off a roof, you don't feel your own weight. So, let's say that you're in an elevator and the cable snaps. And don't do this, but right, you're in an elevator, you're in a falling compartment, You're in an airplane diving downwards at the acceleration due to gravity. You're just letting it go into free fall. All right? If you're in a falling compartment, what will happen? Okay, so against my better judgment, especially because of my recent bout with virus, and I'm not sure I'm actually going to jump here, but I'm going to stand up here, okay? So, right now, hi Kathleen, right now, if I let go of this chalk holder, I'm not gonna, what will it do? It'll accelerate towards the floor. Now, if I jump off the table when I let go of it, how will it move relative to me? What's that?
It'll fall the same way.
It'll fall in the same way, right? It and I will fall, just like all this stuff we were just talking about, will both fall at 9.8 meters per second squared towards the ground. So in my frame of reference, right, attach a coordinate system to me, in my frame of reference, does the chalk fall or does it just hover?
Just hovering.
It just hovers. Relative to me, it's just hovering. It's just hovering there. So really on some level it should be the next slide there, which, oh yeah, I should share the slides because I'm going to start using them here. So share. Desktop 2. Share. And then I should also move this over here. Come on. Give it to me. Where are we? Yeah. Okay, so as kind of illustrated there, all right, we've got you in this rocket that's just kind of firing and just hovering above the surface of your planet, whatever it is. It happens to have the same acceleration due to gravity of Earth, so maybe it's Earth, 9.8 meters per second squared. Al, on the other hand, rockets off. Al is in a compartment just falling freely towards, downwards at 9.8 meters per second squared. Al is weightless. If I step on a scale right now, then the Newtonian picture would be that the scale has to counteract the gravitational force on me, and so it pushes up on me with the same amount of force that gravity pulls down on me, and so as a result, I see a reading on the scale that represents my weight, which is the gravitational force on me, according to Newton. If I do this in a falling compartment, if I step on the scale, what will happen then? Well, the scale is falling at the same rate that I am, 9.8 meters per second squared. Will I have a weight if I step on a scale in a falling compartment? I will not, because in the falling compartment, the scale is not holding me stationary. And so as a result, it doesn't apply a force to me. I'm weightless, and I step on a scale, and I don't push on the scale as a result of that. So I have eliminated the effects of gravity by being in a freely falling compartment. So that's one thing we need to understand, that you can eliminate the effects of gravity by going into a free fall frame of reference. One that is just, if there's a gravitational field around, it just accelerates within the gravitational field so that within that compartment, within the free fall compartment, you've eliminated all the effects of gravity. Just like I was talking about before, in a freely falling elevator, if I let go of something, well, it would just hover in front of me, Just like I would see in outer space if I was floating far away from stars and planets, just in between the stars. Now, here's the part that is going to allow us to understand why it's true that the gravitational mass and the inertial mass should always be the same as one another. So consider the following. Now, instead of imagining that you're in a freely falling compartment, imagine that evil aliens knock us out, and then they secretly take us into a perfect mock-up of this classroom in their evil alien spacecraft, which is accelerating upwards, upwards being defined this way, perpendicular to the floor towards the ceiling, accelerating upwards at 9.8 meters per second squared, the same acceleration as the acceleration due to gravity near Earth's surface. Okay? You are in that compartment, and you hold something out, and you let go of it. So, when you let go of it, is there any force on it? If you're in this compartment, accelerating through space, far from any, let's say we're far from any stars or planets, we're just in the middle of space somewhere, accelerating at 9.8 meters per second squared, you let go of it, so nothing is touching it. Is there any force on it? No, there's nothing to exert a force on it. It has no force on it. Now, the floor and everything else is accelerating upwards at 9.8 meters per second squared, and before you let go of it, that object was also accelerating upwards at 9.8 meters per second squared. What was providing the force on it that gave it that acceleration?
The upward motion.
Not the upward motion.
Your hand.
My hand. My hand is exerting an upwards force on it. My hand's exerting an upwards force on it. When I let go, that force stops. So does it continue to accelerate? No, because if there's no force, what's the acceleration? Zero. So what's true about its velocity? As soon as you let go of it, what's true about its velocity?
Zero.
Not zero.
It'll stay constant.
It'll stay constant. It'll stay constant at whatever its value it was when you let go of it. But the floor, is it keeping a constant velocity? No, it's moving upwards faster and faster, 9.8 meters per second squared. So within the room, in the evil alien spaceship that is accelerating upwards at 9.8 meters per second squared, what happens when you let go of the object? What do you see? You see it fall. You see it accelerate to the floor at 9.8 meters per second squared. Now, fundamentally, is that because there's a force on it? No, there's no force on it. Nothing's attached to it. There's no force on it. So its acceleration is because of the acceleration of the frame of reference. It's an artifact of your observing it in an accelerating frame of reference. So if I have two different objects, different masses, and I let go of both of them in the accelerating compartment, in the evil alien spaceship, compare their accelerations when you let go of them. Are they the same or different?
Same.
They're the same. Because are those accelerations due to a force being applied to them? No. What's the acceleration caused by? Yeah, I think by the why within the room do we see them accelerating?
Because it's like moving towards each other.
Well, I want to go back to fundamentally their acceleration that we observe within the frame of reference of the room is due to the acceleration of the room itself.
Yeah.
Right? Yeah. And is that going to care what the masses are? Right. So in other words, in the accelerating room, it will automatically be true that all objects accelerate to the floor at the same rate, independent of their mass. But there's no mystery there. It's because the acceleration is an artifact of the acceleration of the compartment itself. Right? It's just automatic because the compartment itself is accelerating. And so therefore, everything that you let go of is going to have that same acceleration independent of its mass. Does that make sense so far? Okay, great. So, here's the thing. Now, imagine that I take that object and I attach it to a vertical spring. Is the spring going to do this? Is it going to stretch as a result of having the thing attached to it? Will the spring be stretched by having an object attached to it? Will the spring have to stretch? The answer is yes. Why? Yes?
Because the room that's attached to it is pulling up on it, so it's the opposite almost of the other situation, but it would still stretch the same amount.
It would, yes.
Because the mass still has inertia, and so...
It still has inertia, right? Is it accelerating?
Yes.
It is, because it's attached to the rest of the room, right? So that thing is accelerating upwards at 9.8 meters per second squared. So the spring has got to provide the force on it that will produce that acceleration, right? And so notice that in the accelerating compartment that everything will have the same quote-unquote gravitational mass, right? In other words, we'll get to the point where we, right, notice it says the equivalence principle. You can't tell the difference between being in a closed room on Earth and being in a closed room accelerating through space at 1g. Later, we're going to talk about the strong principle of equivalence. So it says there's no experiment you could perform which would allow you to tell the difference between those two situations, between a uniform gravitational field and acceleration of your frame of reference, of being in an accelerating compartment. And so, in the accelerating compartment, I assert that we wouldn't know any difference, right? If the aliens knock us out and then put us in this perfect mock-up in this room, and then we're accelerating upwards in their evil alien spacecraft at 9.8 meters per second squared, we won't know the difference. And so we could happily weigh things by attaching them to springs and determine, as a result, what we think are their gravitational masses. But what are we really measuring in that case? See, here, when we talked about doing it in this room, in the gravitational field, we argued that we were measuring the gravitational mass because it was the gravitational force that was determining how hard, how much force downwards was being exerted on the block. But in the room that's accelerating, is this experiment determining its gravitational mass, or is it determining its inertial mass?
Inertial.
It's inertial. Why? Yes?
Because it's resisting acceleration of the room.
It's because the what's happening in the accelerating room is the spring is accelerating the mass, right? In Newton's point of view, in this situation, you've suspended the mass. Is the mass accelerating? So if we're just in this room, we're not in the spacecraft, and we hang the block from the spring, is it accelerating according to us? No, it's not. And so what we say is, what's the net force on it? We say, well, the net force is 0 because there is a downwards gravitational force and an upward spring force that are equal and opposite, leading to no acceleration. But in the upwardly accelerating room, what's the description? The description is, there's just the upward force on it due to, well, okay, I have to be careful. Okay, let me kind of write all this out. hopefully in an organized way. Tell me if there's something that you think is missing from your understanding. Because, again, there's a lot of stuff to kind of organize and take in here. And I can see some confused looks and wondering, like, okay, what is the point? So let me just kind of put this all out in an organized way. Okay? So, yes?
Sorry to disturb. Could
Yeah.
you move the camera? So
I could do that. Yes, that would be very nice of me, wouldn't it? Thank you. Anushka's thinking of you, Kathleen. She says thumbs up, okay? Scenario 1. Classroom on Earth. Okay? Hang a block from a spring. See how far the spring stretches. In equilibrium. So, downward force mg, right? Downward force mg. Upward force kx. Mg equals kx. Since, well, let's see. I'll say that again in a minute. If it's in equilibrium, what's the block's acceleration according to us in the room? 0. So no net force. So mg equals kx, and therefore m is kx over g. We have found the blocks. What kind of mass? Did we just find its gravitational mass or its inertial mass? Gravitational mass, because this was based on the gravitational force on it. We just found its gravitational mass. And when everybody's done with this, I'm going to reuse it and I'm going to turn it into scenario 2, classroom mock-up in evil alien spaceship. But first I want everybody to be done so that I can erase it. And not have it in the way of, well, I want Kathleen to be able to see what we're doing here too. Okay. All right. Actually, you'll have plenty of time because we'll take our break right here. there's this hump I got to get you past of understanding this idea of why this is a mystery and non-inertial reference frames and so forth. All right, onwards and upwards here. Okay, so now let's make some small yet very significant modifications to this to account for being in scenario 2. Classroom mock-up. In evil alien spaceship. Accelerating upwards at G. Accelerating upwards at G. Okay? So, let's hang a block from a spring and see how far the spring stretches in equilibrium. What's the downward force on our block in the evil alien spaceship? Or is there one? There is none. There ain't no gravity there, we say. So the downward force equals 0. We change it to, this time, equals 0. What's the upward force on our block attached to our spring, stretched by an amount x? So what is it equal to? Is it any different from here? Is it different from kx, or is it kx again? It's kx again, because it's the spring stretched by amount x, and so k is the spring constant, kx is the upward force. So, what's the block's acceleration in the evil alien spaceship? Yeah, the whole thing is accelerating upwards at g, so the block's acceleration now is g instead of 0. Notice this is why we would say, kind of looking from the outside, seeing the room accelerating upwards at g. In the room itself, we would say, well, the block's just sitting there, just like we do on Earth. But this is the point of view of outside the room, watching everything from the outside. So the block's acceleration is g. And so now we say that the mass times the acceleration, but we know the acceleration is g, is mg. Why, that must be equal to the force on the block. So again, we get mg equals kx. And so we would again say, okay, m is equal to kx divided by g, just like before. And we have found the block's what kind of mass in our experiment? Inertial, because it was the acceleration of the block that was being involved here. And we have found the block's inertial mass. Well, notice we would get exactly the same value either in the evil alien spaceship or here on Earth, right? We get kx over g as the mass of the block, but in one case we said, well, that was a way of determining its inertial mass, and in another case, with the identical experiment, we said we were finding the gravitational mass. But the thing is, in the accelerating compartment, again, as we argued, we are automatically going to find that every object will have the same acceleration if we let go of it, because it accelerates to the floor due to the motion of the frame itself. So let me know when I can erase all this, because I know, I just got to erase a few things, and you probably have to write it all again or something like that. But let me know when I can erase this, and then we will proceed forth. Yes. Yes.
Diagram for this.
Oh, yeah. That's an important point. Thank you. Yes, because I should have fixed this. Right. So the diagram, I meant to do that. Thank you. Right. The free body diagram is different now. The free body diagram is now just Kx is the only force on it, because there is no gravity force in this scenario. Now there's an unbalanced force, we say, acting on the block. Some of our Newton, this is nothing Newton couldn't say too. We haven't done anything that Newton couldn't say. But we will now start to make explicit Einstein's big revelation, right? Seemingly simple things can be very profound and take geniuses to realize their implications fully for the first time. Can I erase it yet? Can I do it? Anybody going to stop me? It's going to, Okay. Okay, so let's distinguish inertial and non-inertial frames of reference. An inertial frame of reference is one where the law of inertia holds. You're like, what are you talking about? The law of inertia is universal. Ha! Is one where the law of inertia holds. In other words, an object with no force on it has no acceleration. But Dr. Harmon, Newton's second law says that, and that's just like Newton's first and second laws. How can there be anything other than an inertial frame of reference? Why, sure there can. So, what's an example of a non-inertial frame of reference? Yes?
An accelerating frame.
An accelerating frame, exactly, right. In the evil alien spaceship, right, if you let go of an object, is there any force on it? No, but in that frame of reference it accelerates to the floor, right? Zero force, non-zero acceleration. In an accelerating reference frame, an object with no force on it will accelerate relative to the frame. It's almost like relativity is involved here. Relative to the frame due to the acceleration of the frame itself. So accelerating frames are non-inertial. An accelerating frame is a non-inertial frame of reference. Profound question. What determines which frames are inertial? If you figure it out, please invite me to see your Nobel Prize being given. Please invite me to see you receive the Nobel Prize. Because you will receive the Nobel Prize for this, if you were to figure this out. Nobody knows the answer to this question. Nobody knows. So, because if you think about it, right? We talked about the EVO alien compartment accelerating upwards at g, right, in the spacecraft. Accelerating with respect to what? Right? If I have two rocket ships next to one another, and one has its engines off, we're far deep in space, far from any stars and planets. One's got its engines off, the other one's firing its rockets. Well, is it not true? So first of all, which one would we say is the accelerating frame?
When you're not in.
No, but I mean, what? So I'm giving you a choice. Two rockets, not firing the engines, firing the engines. Which one's the accelerating frame?
Firing.
The one that's firing its engines, right? But isn't it true that relative to that rocket, the other rocket is accelerating in the other direction? So why is it the one that's firing the rockets the one that is accelerating? If you think about it, you might, why? Nobody knows why exactly, believe it or not. Nobody has a really convincing answer. So in practice, if you are in a compartment deep in space and you're not firing any rockets and you look outside and the stars are not rotating around you, you don't see the entire universe rotating around you, you will be in an inertial reference frame. And that's, just from a practical standpoint, that's something we can say. In practice, inertial frames, I'll say just what I said. In practice, a compartment, right, like a room in deep space, with no engines firing. If it's got engines attached to it, and which does not see the stars spinning around it, will be an inertial frame. If the stars are spinning around you, you'll have centrifugal force in that frame. But if you're in deep space and the stars aren't spinning around and so forth in practice, that's going to be an inertial frame. do experiments, you would find no force, things move in a straight line at constant speed, etc. If the stars are spinning around you and you launch something, you'll see that it appears to follow a curved trajectory in your frame. Because of the rotation of the frame, it'll be moving straight relative to a frame that's not spinning with respect to the distant stars. And within the frame, you'll see things as a result following curved trajectories due to centrifugal and Coriolis forces, quote unquote. Frames moving in straight lines at constant speed. And not rotating with respect to that frame will also be inertial. While all others are non-inertial. Right, so if with our rockets in space, right, it's the one without the engines firing, as long as it's not spinning with respect to the distant stars, that'll be the inertial one, and the one with the engines firing will be the one that's non-inertial. Once you've found an inertial frame, you got all the other ones. It's everything is moving at a constant speed, in a constant direction with respect to that one, and isn't spinning with respect to it. That's also an inertial frame. And then everything else is non-inertial. But what picks out the inertial frames in the first place? How does a frame know to be inertial, so to speak? Einstein wanted to know. Nobody knows. There's an idea called Mach's principle that says that the inertial frames are somehow determined by the overall distribution of matter and energy in the universe. And that seems to be basically right, but nobody knows precisely what that means or how it's done, essentially. But the idea that if you're not rotating with respect to the distant stars, for example, gives that sort of idea of, well, if the universe isn't spinning around you, then you're in an inertial frame, as long as you're not firing rockets. If the universe isn't spinning around you, well, if the universe isn't spinning around you kind of gives the idea of, oh, it's somehow the overall distribution of matter and energy of the universe that's telling frames whether or not they should be inertial or not. Frames that are spinning with respect to the overall distribution of mass energy in the universe are not inertial. So Mach's principle, which is only kind of hazily formulated, is inertial frames are somehow determined by the overall distribution of matter in the universe. Matter, energy in the universe. Right? If you think about it, right, we're touching on profound questions here, kind of deep philosophical, metaphysical questions here. How does the universe know which frame should be inertial and which frame should be non-inertial? When you're in freshman physics, you learn Newton's laws, and you don't even think about things like inertial frames versus non-inertial frames. But you know, you're ready for that sort of thing. You see a taste of that in Physics 280 as well, of course. Yes?
So isn't that pretend to think everything in the inertial frame has to be stationary?
No, certainly not, because if I'm in space in some inertial frame, I can certainly throw things around and move them and so on and so forth. So that's fine.
But then why do we say it's based on the distribution of matter and energy?
So in other words, the frame itself, so stuff within the frame might be moving around for sure, But I'm talking about, right, on some level, you can imagine marking off a frame of reference with coordinate axes, right? And so if you imagine, kind of boil it down to coordinate axes, right? So take 3 of these things and make an x, y, z coordinate system, okay? And stick that out somewhere, all right? If you don't have rocket engines attached to it, you just put it far out in space somewhere with no rocket engines attached to it. As long as the 3 coordinate axes are pointing straight and true to distant points, such that if you were looking along one of those axes, you didn't say, oh, look, there's Canopus. Oh, first it's to the right of my axis, and now Canopus is to the left of my axis. Wait, what's going on? Canopus keeps on going. Well, then, oh, wait a minute. I must be rotating with respect to the distant stars. If the coordinate axes are not doing that, if they point straight and true to the same distant stars, and they don't have rocket engines attached to them to give them acceleration otherwise, you just found a set of 3 coordinate axes that are defining, if you will, an inertial frame of reference. You make measurements of particle positions with respect to those 3 axes in experiments in your compartment. If they're like, attached to the walls of your compartment, then the experiments you're doing in that compartment are being done in an inertial frame of reference. And that's kind of the idea there. Does that make sense? No. Okay. Do you have a question about that might tease it out, or maybe we talk about it later, or what?
So you mentioned that in the previous frame, the star was moving with respect to you.
Right. You see it spinning around you slowly, right? Imagine you're deep in space, and you see the whole sky spinning around you. That would say you're rotating with, that would mean, right, is the universe rotating or are you? Well, it's easier to say, well, I'm probably the thing that's rotating, right? So if you see the universe spinning around you, you say, oh, I'm rotating, and I'm not an inertial frame as a result of that. If I make measurements, if I launch things away from me relative to those spinning coordinate axes, they won't move in straight lines. If I launch something and it's moving in a straight line with respect to the distant stars, but my coordinate axes are rotating, then relative to those coordinate axes, it'll be executing a spiral because of the rotation of the coordinate axes. So that's not an inertial frame. No force, and yet it's executing a spiral, which is accelerated motion. Okay, alrighty? Yep, okay. Okay, so I'm going to assume everybody's had time to copy this, all right? So now that we've got the idea of inertial versus non-inertial frames of reference, we say in a non-inertial, I guess I'll hyphenate, non-inertial, uniformly, in the non-inertial, uniformly accelerating rocket ship frame, actually I'll say A, I want to be generic here. In a non-inertial, uniformly accelerating rocket ship frame, doesn't have to be a rocket ship obviously, and it doesn't have to be something physical. You can just imagine coordinate axes that are accelerating in your mind. All free objects, ones that are not interacting with anything, nothing's touching them or whatever, all free objects accelerate towards the floor at the same rate. So now we are in a rocket ship. Accelerate towards the floor at the same rate minus A, so I'm going to be generic. Instead of saying G, let's let the acceleration be anything we want. It doesn't have to be 9.8 meters per second squared, where A is the acceleration of the ship, and I'm giving it a vector. It could be in any direction. Right? So, for example, in the evil alien spaceship, the direction of the acceleration was which way? If we're in the evil alien spaceship, what's the direction of the acceleration of the frame? Up. So we therefore see everything accelerate which direction? Down, the other direction, right? That's the idea here. That's the idea of minus A and A, where A is the acceleration of the ship. So each object experiences a fictitious or inertial force minus ma. It's like bookkeeping, if we will. A fictitious or inertial force minus ma. How many of you have had 310 mechanics? Okay, did you talk about inertial forces? Like centrifugal force, all that sort of thing? Because this is what we're talking about here. An inertial force minus ma. Right? In other words, everything seems to have this force minus ma on it that gives it its acceleration minus a towards the floor. A mass attached to a spring stretches the spring by an amount proportional to the mass. Just like we talked about. Right? If I have a heavier mass attached to the spring, to give that, well, I shouldn't say heavier. If I have a larger mass attached to the spring, to give it that same acceleration requires a bigger stretch of the spring because you got to put more force on it. So a larger mass stretches the spring more, just like happens in a gravitational field, by an amount proportional to the mass. All these effects arise from the fact that the frame is non-inertial. This is crucial. All these effects arise because the frame is non-inertial. And here's the crucial thing. It is just as though there were a gravitational field with gravitational acceleration minus a in the rocket ship. It is just as though there were a gravitational field with gravitational acceleration minus a inside the ship. In other words, we're in the evil alien ship Okay, we said A was G, but it doesn't have to be. It could be simulating gravity on Mars or something like that. Doesn't matter. The point is, it would seem to us like we were in a gravitational field, right? If we wanted to pick some, if I'm in that rocket ship, if I want to hold something, I need to exert an upward force on it in order to give it the acceleration of the rocket ship. So it feels like it has weight to me. I have to hold it up. I need to exert a force on it in order to hold it up. If I step on a scale inside the rocket ship, do I have weight? If I'm on the rocket ship, I step on a scale, yes, because the scale has to give me my acceleration. So it has to push up on me to give me my acceleration. Instead of saying that it's counterbalancing the force of gravity on me, we say, no, it's giving me my acceleration, mg, where g is the acceleration of the compartment. So I weigh things on, I will step on a scale and have a weight, just as though I were on Earth. So the point is that it's like you're in a gravitational field here. Everything wants to accelerate towards the floor, independent of its mass, just like in a gravitational field. Things have weight, just like in a gravitational field. And Einstein says it's not just like it's a gravitational field, it is a gravitational field. Einstein would say that there is a uniform gravitational field in the rocket ship. Can I erase this yet, or are people still? Okay. Maybe I am just going to move Kathleen. Oh, no, but are you done writing, Kathleen? Kathleen is done writing. Okay. I'm going to take Kathleen over here. Come with me, Kathleen. Here we are. Okay. Okay. All right. Einstein made the leap of saying that there is a uniform gravitational field in the rocket frame. Not that it's like there's a uniform gravitational field, that it's the same thing as a uniform gravitational field. That there is a uniform gravitational field in the rocket frame. And on the flip side, as we've also seen, the effects of gravity, the effects of a uniform gravitational field are abolished in a frame in free fall. The effects of a uniform gravitational field are abolished in a frame in free fall. You can eliminate gravity. And this is what made Einstein decide gravity is not actually a force. From these considerations, Einstein concluded that gravity is in fact an inertial force. It's a fictitious force that exists because of observing in a non-inertial frame of reference. Yes?
Doesn't that kind of contradict what he later says about how gravity, like gravitational field is just the bending of space-time?
No, it doesn't contradict it at all, actually, as we'll see. We'll get there. Yeah, it doesn't contradict it at all. It's entirely consistent with that. It's not that he's saying that gravity doesn't exist, certainly not. It's just that what we call the gravitational force on an object is actually an inertial force. It's a fictitious force, an artifact of observing in a non-inertial frame of reference. In other words, this room is a non-inertial frame of reference, and the inertial frames are the ones that are in free fall towards the center of the Earth. And the reason why we see things appear to fall, well, they don't appear, they really do fall to the floor, is, well, we'll get there. Let me just keep going and then we'll get there. So, from these considerations, Einstein concluded that gravity, in fact, is an inertial force. I'll put it this way, that gravitational forces are actually inertial forces. The inertial frames near Earth's surface are in free fall acceleration towards the center of Earth. Are in free fall acceleration at 9.8 meters per second squared towards the center of Earth. Either straight towards the center, that's the easiest to conceive of, or in almost elliptical orbits. I say almost because in general relativity, the orbits aren't ellipses, but they're damn close near Earth. So, yes?
On the first line, the word before is it there?
Which one? How high up am I?
That first, that one.
Einstein made the leap of saying that that there is a uniform gravitational field in the rocket frame. Yep. Okay? So I'm going to skip ahead. Go ahead. No, not yet. Not yet. So, in other words, the idea is that, and these are the easiest ones to picture, the inertial frames are the ones that are in free fall towards the Earth's center. So, in other words, a compartment that you just drop is an inertial frame of reference. And so, if you let go of something in the freely falling compartment, what will it do relative to the compartment? If you're in a closed compartment, it doesn't have to be closed, but if you're in a compartment and it's in free fall towards their surface, you reach out with something and you let go of it, what do you see it do within the compartment relative to you and the rest of the compartment? It just hovers, right? It just hovers. Is there any force on it? So we have to be careful. Would we normally say, if we have Newton's point of view, is there a force on it?
Holding it?
If I let go of it, Newton's point of view, be Newton for a minute, I let go of it, is there a force on it?
Yes.
What force?
Gravity.
Gravity. We'd say there's gravity force on it. And we would say, I know, you got to think very carefully, right? You say, oh, there's a gravity force on it, and what's happening is it's accelerating to the center of Earth due to the gravity force, but you don't notice the acceleration because you are too, blah, 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 blah. But now we have to change our point of view. Here's what Einstein says. Einstein says that there's never a gravitational force on it. Gravity is not a force on it. So in the freely falling frame of reference, when you let go of it, there's no force on it, because gravity is not a force. Bear with me, gravity is not a force. There's no force on it. And if there's no force on something, describe its motion. Does it accelerate if there's no force on it?
It does not.
It does not. And is it accelerating in that freely falling compartment?
It does not.
It is not. So Einstein says that's the inertial frame. There's no force on it, and it's not accelerating. Okay? But if the freely falling frames are the ones that are falling at 9.8 meters per second squared towards the center of Earth, what is our room doing relative to such a frame? Describe the motion of our room relative to, yes, our room relative to the freely falling frame moving at 9.8 meters per second squared faster and faster towards the center of Earth. Our room is accelerating upwards at 9.8 meters per second squared. Now, I'm not saying it's moving further from the center of Earth. It's certainly not. But in other words, relative to the freely falling frames, the surface of Earth is always instantaneously accelerating upwards at 9.8 meters per second squared. Can you buy that? Do you see what I'm getting at there? If the frames are accelerating downwards relative to us, then that means that relative to those frames, we're accelerating upwards. And if those freely falling frames are the inertial ones, what do we say about a frame that's accelerating with respect to an inertial frame? Is that frame inertial or is it non-inertial?
Non-inertial.
It's non-inertial. So the frame of Earth, a frame attached to Earth's surface like our room is a non-inertial frame of reference. And if I let go of something, there's no force on it because gravity is not a force, and yet it still accelerates to the floor. Why is it accelerating towards the floor? So there's no force, but it's accelerating towards the floor. Let's go into outer space again. In the Evo alien rocket ship, where the room is accelerating upwards at 9.8 meters per second squared, I let go of something and it accelerates to the floor. Why is it accelerating towards the floor in the Evo alien rocket ship? Because the floor is accelerating upwards. Now I'll come back to Earth again. Is the floor accelerating up? Is our floor accelerating upwards relative to inertial frames?
Yes.
It is. So if I let go of something, there's no force on it because gravity is not a force, and yet it still accelerates to the floor. Why is it accelerating towards the floor?
Because with respect to the inertial frame, we are moving upwards.
That's right, because the floor is accelerating up to hit it. The floor is accelerating upwards. It's an artifact of viewing in a non-inertial frame of reference. That's the key that you have to wrap your head around, is that according to Einstein, the gravitational force is just a fictitious force. Just like if we're in the accelerating compartment in the rocket ship, et cetera, we could invent a fictitious gravitational force, if you will. We could pretend there's a downward force on every object, in order to account for the fact that every object accelerates towards the floor. We invent this fictitious gravitational force inside the rocket ship. Einstein says that's what we're doing on Earth. That the inertial frames are the ones that are in free fall, but we're doing everything in this non-inertial frame of reference, and so we invent this fictitious gravitational force on everything to account for everything accelerating towards the floor, but what's really happening is the floor is accelerating up towards them, if you will. Again, not that the floor is literally getting further from the center of the Earth. Those free fall frames are just falling through the Earth's surface and keep on going towards the center of the Earth. And there's an infinite number of them moving every which way. You can pick any one that you like. But the point is, Einstein says gravity forces are fictitious forces, just like the ones in the rocket ship. That's the profound point of view. Questions? You got to think about this carefully. It's a lot to wrap your head around, but that's the big leap that Einstein made. That's why things fall to the floor. It's because, it sounds kind of Zen or something, right? Or something like that, right? Newton says that you fall to the floor, right? Einstein says, no, the floor falls to you, so to speak, right? If I jump off the table, the floor is rushing up to smack me, not the other way around, if you will. Cool. Profound. That's Einstein's big. That's the big picture that we have to get here. Okay? How many minutes do I have left here? Okay. So I will share with you. How can we get here? Back. Yeah, okay. So, yeah, we've talked about this idea that you could eliminate, right, the flip side. The effects of a uniform gravitational field are abolished in a frame in free fall, okay? That's one version of what's called the principle of equivalence. This is my favorite video that describes that shows that version of the principle of equivalence. So here's two folks in an airplane, and they're going to go into a free fall dive. They're just going to kind of point towards the ground, go on a parabolic trajectory, and just allow themselves to just free fall towards their surface, thereby eliminating the effects of gravity within the airplane so that everything becomes weightless within it. And this is what happens. He's like, I'll nibble your ear. And then whoops, it came out of the fall, but, right? Okay. And then one more thing. Do y'all know OK Go?
I was going to mention.
Yes. Do you know OK Go? So it's a group. You can't be a physicist or astrophysicist without watching every possible video made by OK Go, because it is made for people with STEM appreciation, all right? And they made a video in the equivalent of, as a commercial one, I think, the Vomit Comet. So that's an airplane that NASA uses. This isn't the Vomit Comet, but it's one that does that kind of thing. You can train astronauts for weightlessness by going for like 30 seconds at a time. You can go into free fall in the plane, so it keeps following these like parabolas. And so when you come up again, all of a sudden there's gravity again. But let's eliminate the effects of free fall in a freely falling compartment for several minutes. This is how we'll play ourselves out here. I'll have to cut this. Oh, I better cut that out of the video now, because this will get a strike.